All right, this is the example program unit F1, page 7. Let's take a look at the laminar flow solution of a pipe flow. This is a glycerin at 20 degrees C, flows upward in a vertical 75 millimeter diameter pipe with a center line velocity of 1 meter per second. Determine the head loss and pressure drop in a 10-meter length of the pipe. All right, this is a good program. So this is the picture of a vertical upward flow of glycerin at 20 degrees. Now obviously, in order to make this kind of flow, you have to have a higher pressure and lower pressure. Then this pressure difference goes against the gravity so that the flow is going upwards. Okay. What is the first thing you want to do? I guess first thing I want to do is to find out if this is laminar flow or turbulent flow. Most likely this is laminar flow because the program says so. But let's just check. Okay. Suppose if this is a laminar flow, laminar flow of a pipe comes with very smooth distribution of the velocity within the cross-section represented by parabolic function. Obviously, the velocity is maximum in the center of the pipe. Now, in this particular program, this is BC. So in this case, center line velocity is given by 1 meter per second. Okay? So this is a parabolic function. Velocity is 0 on the wall, maximum in the center. If this is a parabolic function, you can actually determine the average velocity. Okay? This is B over bar called average velocity. Average velocity of a parabolic function of velocity distribution is simply 1/2 of BC, which is 0.5 meter per second. This is the average velocity across this probably laminar flow of the pipe. But anyway, rather than using center line velocity, I want to use the average velocity to find out the Reynolds number. Okay. So let's check the Reynolds number. Reynolds number is density, velocity, diameter divided by viscosity. The density of the glycerin 20 degrees C, you have to look up the property table, but this is the property of glycerin, density, viscosity. Okay. So let's just plug in 1,260 kilogram per cubic meter for the density. Velocity, I'm going to use average velocity, 0.5 meter per second. Diameter is 0.075 meter. This is given 75 millimeter diameter pipe. Viscosity is here, glycerin viscosity at 20 degrees C, 1.5 Newton second per meter square. This is going to give you Reynolds number 31.5. Whoa, this is really low Reynolds number. Much less than 2100, so definitely this is laminar flow. Okay, that's good. So we are going to employ laminar flow analytical solution. Let's go back to the previous page. Take a look at 3 equations given here for a solution of analytical solution of laminar flow. So 3 equations. First equation relates the shear stress to pressure drop. This one relates the velocity to pressure drop. This is a flow rate to pressure drop. So I'm going to pick up equation in the middle. And then keep that in mind for upward flow. Vertical. Flow is vertically upward. So say that it's 90 degrees. So within that equation, you need to plug in theta equals 90 degrees. So the equation now becomes velocity is delta p minus gamma L sine theta multiplied by diameter squared divided by 32 mu L. If you plug in theta equal to 90 degrees, this becomes delta p minus gamma L sine gamma L times d squared 32 mu L. Okay? So let's solve this equation for delta P. Delta P now becomes 32 mu L times B. 32 mu L times B divided by diameter squared plus gamma times L. So if you plug in 32, viscosity is given 1.5 Newton second meter square. Length is 10 meters. Velocity, let's use average value, 0.5 meter. Divided by diameter 0.075 meter. This thing square plus gamma of glycerin is density times gravity. So 1,260 kilogram per cubic meter multiplied by 9.8 meter per second square. Gamma is rho g, okay? Rho times g. Length is 10 meters. This is going to give you 166.67 times 10 to 3 Newton per meter square. This is 166.67 kilopascal. Okay, so this is the pressure drop over the length of 10 meters. So obviously this is high pressure, low pressure, but over the 10 meter length you are going to lose 166 kilopascal of pressure. Okay. Also, what is the heat loss for this case? All right. So once again, we are going to remember the energy equation. Remember unit D3. Okay, so unit D3, we know that energy equation of a pipe is plus HS minus HL. Now this is energy equation we know. Now this is just a pipe. Okay, so we do not even consider the shaft. So for the pure pipe system, this is the energy equation. Now we do know delta P. Now this delta P is pressure drop between 1 and 2, so P in minus P out, right? Okay? So, and also another thing is, this is constant cross-section pipe flow. So if you apply continuity, if the cross-section area is constant, and this is incompressible, density doesn't change. So that means velocity doesn't change. Velocity is uniform. Velocity is constant here, 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 here. So velocity V1 equal to velocity V2. Velocity V in equal to velocity V out. So you can cancel out V in, V out, saying V in is equal to V out. Continuity. Remember unit D1, okay? So continuity actually drops you off this term. And another thing, Z out minus Z in is equal to 10 meter. And then P in minus P out is equal to delta P. Then we do know what the delta P is, okay? Therefore, from this equation, you can determine head loss. So head loss becomes P in minus P out over gamma minus Z out minus Z in. We do know this is delta P, which is this one, so let's just plug in. 166.67 times 10 to 3 Newton per meter squared. Specific weight is rho G, 1,260 kilogram per cubic meter times 9.8 meter per second square. So that's this term. And minus Z out minus Z in is 10 meters. Okay? So HL is 3.44 meters. So we just found two very, very important things about this flow. Laminar flow or particle flow, the pipe. This is called pressure drop. Pressure drop is along the direction of the flow of the pipe, how much pressure change happens. This is important because this is going to determine how big your pump should be in order to make this flow happen. If this is a large value, you need to have a big pump to achieve this kind of vertical flow. And then obviously, this is going to determine how much head loss you actually have. This much. Okay? This is the loss associated with the pipe flow in this case. Okay? It's essentially a function of delta P. If you have a big pressure drop, you have a lots of head loss, you need to add huge pump to add more energy to deliver the liquid upwards. Okay? So obviously in unit F, our major concern is how can we minimize this head loss? That's our major concern. So if we achieve a small head loss in pipe system, it is going to save lots of energy, tons of energy. Okay? So the major concern usually for the pipe flow design is how can we minimize the head loss. Okay? So we're going to take a look at it in unit F1, F2. Let's stop here.